I know I took a pretty long time to post this, but we have about 3 coming soon. So, this is Intro to Algorithms. Today we'll be discussing insertion sort. Now, although this may not be the best sorting algorithm, it is partially efficient due to the fact that it does preserve positioning. What does that mean? That means that if 1, 2 originally is before another identical 2 in a list, then that 2 will always be first relative to the other 2. These can come in handy when you deal with implementing structures that's supposed to somehow retain positioning, like queues, things like that. But yeah, there are many applications, and sometimes insertion sort, especially used on small small lists or arrays, can come in handy. You also can use insertion sort in combination with other algorithms. For example, merge sort. Maybe you don't want to completely recursively go down to one single element in merge sort. Maybe you want to only go down to list size of 3 or less than 3. And once you get down to that threshold of a length of an array, then you can use insertion sort, which would be rather quick. So let's go on. Today I will discuss intuitive approach to understanding insertion sort and simply analyzing the runtime. So what is the understanding behind insertion sort? The best way to explain it is sorting a deck of cards, right? Specifically from right to left. Whereas, you may go through each card one by one from left to right, but you're going to continuously sort them from right to left, right? Try and think about how you naturally scan over your hand of cards. Maybe you're playing spades, bid whist, crazy eights, whatever game you like to play. You sort of scan over each card, right? For each card in your hand, you'll compare it to the previous elements that you've already sorted, right? That's the invariant of the situation, that anything before the current card is already sorted. Using this, it's rather easy to make this algorithm or to do this algorithm. I think it's most intuitive for new programmers or new algorithmic thinkers, and fairly easy to implement, not too many lines of code. As I was saying before, or as I stated before, this was not the most efficient sorting algorithm, but it does work relatively well on small data sets and their inputs. So this is just a view. Say you wanted to sort this, and we say that A is to be equal to 1 rather than 11. So you say, okay, 1. Well, that's by definition already sorted because nothing else is before it. J. Oh, is J greater than, or better yet, is A greater than or less than J? It's less than. Okay, fine, move on. 2. Is J less than or greater than 2? It's greater than, so let's shift it over. We'll shift it here. The 2 will come in front. Is A less than or greater than 2? It's less than, so you keep it in that position. Then you'll have A to J, and so on and so forth. I'll explain this a bit more visual later on, but let's quickly go to the pseudocode and sort of understand the runtime behind this. I'll let you digest that for a little while. So as you saw, the way I was sort of stepping through the card example, we'll define insertion sort. We'll loop over every element in the array A, right? So let's set this value to be equal to whatever current position we're at. Then we make the first pointer equal to the card to the left of it, right? And while this pointer is greater than 0, which means that it can't go beyond the last element, or the first element of the array, and this element that's at that position is greater than or equal to the value, move it over. Now this equal sign would not hold to the way we sort of explained it prior, where you sort of maintain the positioning, but all you have to do is simply delete the equals for the specific, for my specific usage. I wanted it to be equal, but all you have to do is take out the equal sign and you'll preserve the queue aspect, right? You'll preserve when those elements occurred in the list originally. So while you're not beyond the first element in the list, and that element that you're looking at is greater than the value that you currently have, you want to switch those values, right? So you add 1 to I, you make that equal to what I currently is, you decrement I to look at the previous value, and then you set, or you continuously do this, and then at the very end, when you finally are finished with I, you set I plus 1, that positioning, to the value that you originally started with. And then once you go through the entire loop, through every element, you'll return the new sorted array. Another good aspect about this algorithm is that it's done in time or in space, which means that you're modifying the actual array rather than having to take up extra space, which merge sort does. That's just an example of an algorithm that takes up a lot of extra space and memory allocation. So to analyze this, let's think. So you have to go through every number in the array, or every element in the array, and for every element you need to then loop through every other element prior to the element that you have. Now we don't actually have to add this up, but if you think of 2 for loops, which is simply what this sort of is, what type of runtime would you have? Right? Like just by mathematical terms, for each, right? So it's like saying, for each shirt that I have, let me pair it to the number of pants I have. So I have 3 shirts and 3 pants, I have 9. Same thing with this. You have n elements in the array, and on average, or at the bottom, the leaves of the tree, if you were to draw this out, at the leaves or base of the tree, you'll be basically looking at every single element. On average, you'll look at almost the entire array in order to sort it. And so you just do n times n. Now I'll show you a quick example. I'm not going to go through the entire example, but I will do enough so that you sort of get the gist of how it will work. So say we begin with this array, correct? So let's use our method. First, we pick the first element, or let me say the index 1 element, which would be 3, and we do I is equal to j minus 1, where j is equal to 1 right now. So now j minus 1 is 0, which is this guy. So is 10 greater than 3, or greater than or equal to 3? Yes, it is. So now you swap them. Or better yet, you move 10 over. Because I is now equal to 0 and not greater than 0, you're done. So now you have the new array, 3, 10, so on and so forth. Next step, you get 5, because now you're at j is equal to 2. Now I is equal to 1. Is AI, which is equal to 10, greater than 5? Yes, it is. So now you move it over. Is 3 greater than 5? No, it's not. So now you can exit the loop. Now you're stuck with 3, 5, and 10. You do the same thing with 8. You compare 8 to 10, and then 8 is compared to 5. You're done. Now this is the interesting case for 2. 2, as I was saying, why it ends up becoming n squared on average is because this 2 will be compared to 10, then 8, then 5, then 3, and end up all the way here. And as you can see, the 1 will have to do the same exact thing all the way down. And of course, the 0 would have to go all the way down. So as you can see, our understanding of the algorithm's runtime would on average be correct. Especially worst case scenario where the original array is literally sorted backwards. So if we had 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, that would especially take n squared time. So that is all I have for today in terms of or on insertion sort. I hope you understand that tutorial and sort of develop an intuitive understanding of how insertion sort works. Thank you.